Assalamu alaikum students. I hope you are all fine by the grace of Almighty Allah. I welcome you all to the fifth lecture of Thermodynamics 2. Lecture 5. Contents of lecture 5 are mass balance for steady flow system, steady flow energy equation, steady flow energy equation versus Bernoulli's equation, introduction to nozzles, numerical problems, conceptual question and answers. Mass balance for steady flow systems. First, we will discuss about some basic definitions of different types of systems. So the first one is non-flow process. Process occurring in closed system which do not permit mass transfer across their boundary. So you can compare non-flow process to closed systems as mentioned here. Therefore, mass cannot transfer across their boundary. However, during non-flow process, energy and work can cross boundary. Flow process occurring in open system which permit mass transfers across their boundary. So in flow process in open system, mass is allowed to transfer boundary as well as energy and work. So steady flow process. Thermodynamic property have a fixed value at a particular location and not change with time. They are fixed in space, time and shape. So thermodynamic properties like temperature, pressure, mass flow rate, specific volume, all these are the properties of the system. Therefore, in steady flow process, they will not change with time. Even energy, the rate of energy in is equal to energy rate at the outlet. Non-steady flow processes, or they are also known as transient flow process. Thermodynamic property varies with time or change with time. They are not fixed in space, size and shape. So in transient flow process or non-steady flow process, E energy flow in minus energy flow out is not equal to 0, whereas here E in is minus E out is equal to 0. Similarly, mass flow in minus mass flow rate out is not equal to 0. We will discuss these processes in detail in upcoming lecture. Total amount of mass contained within control volume does not change with time. So this is talking about steady flow system. Steady flow process. Total mass entering the control volume is equal to total mass leaving the control volume per unit time. So mass flow rate, this is applicable for steady flow. And in unsteady flow, this will have some value. As you can see that there must be an amount of mass transfer in non-steady flow process. You can understand it more easily that if the process is steady, 2 kg mass per second is entering, then 2 kg mass per second will be, mass flow rate will be out at the outlet. However, in non-steady flow process, there might be instant for non-steady flow process, there must be an instant where 1 kg or 1.5 kg per second mass is getting out. That's why the change of mass flow rate is shown here. So this is the continuity equation, or you can say that mass flow rate in is equal to mass flow rate out. So we will derive a relation here. So density is equal to mass over volume, therefore you can say mass is equal to density into volume. So on both hand side we have divided the equation with time, and volume is equal to cross sectional area into length. So mass divided by second here, and on the right hand side that is density, cross sectional area, and this is velocity. Length or distance divided by time is equal to velocity, which is represented by small c. I have used small c to represent velocity so that students should not get confused it with specific volume or volume. To distinguish this velocity with specific volume, I have used small c symbol. In book you might see that the author has represented the velocity with this or bold V. So you should not get confused. I have mentioned here also that C represent velocity. So mass flow rate is constant. Left hand side mass flow rate, this value is constant. Therefore we can obtain a relation rho 1 A1 C1 is equal to rho 2 A2 C2 at any instant throughout the process, where rho is the density of the substance, A is the cross-sectional area, where C is the velocity. As you know that density is equal to mass over volume, and density over mass is equal to 1 over volume. Specific volume is equal to 1 over density. So we have replaced the density with the specific volume. This is the volume divided by mass. So the relation we have obtained is A1 C1 over V1 is equal to A2 C2 over V2. A is the cross-sectional area, C is the velocity, and V is the specific volume. So now we will solve a numerical problem. The statement of the problem is air is flowing in a 0.2 meter diameter pipe at a uniform velocity of 0.1 meter per second. The temperature is 25 degrees centigrade and the pressure is 150 kilopascal. Determine the mass flow rate. So there is a pipe. The values are, I have underlined the values. Diameter of the pipe is mentioned, velocity and the temperature. In thermodynamics, you should always remember that wherever the word temperature is mentioned, all the formulae are used for the absolute temperature scale. Therefore, if a temperature is given to you in Celsius scale or Fahrenheit scale, you should convert it to in Kelvin scale. Now, this is the relation we have derived in the previous slide. M dot is equal to AC over V. A is the cross-sectional area, C is the velocity, and V is the specific volume. We also know that this is the equation of state. PV is equal to mRT. We have divided this M with on the left hand side, and pressure into specific volume is equal to RT, and specific volume is RT over P. For air, we know that specific gas constant value is 0.287. Temperature, we will convert this into Kelvin scale by adding 273 in the Celsius scale temperature given, divided by 150, which is the pressure mentioned in this statement. So specific volume is 0.057 meter cube per kg. Now the formula for area is pi d square by 4. The value of diameter is 0.2. Therefore, the area comes out to be 0.0314 meter square. Now we will insert all these values into the main equation. M dot is equal to AC over V. Therefore, our mass flow rate comes out to be 0.0055 kg per second. Another numerical problem. A hot air home heating system takes 0.25 meter cube per second air volume flow rate at 100 kilopascal pressure, 17 degrees centigrade into furnace and heat it to 52 degrees centigrade. That is the inlet temperature 17 degrees centigrade and the outlet temperature is mentioned as 52 degrees centigrade, and delivers the flow to square duct 0.2 meter by 0.2 meter at 110 kilopascal. That is the outlet pressure. What is the velocity in the duct? So the main equation is, that is the relation for specific volume. So mass flow rate is equal to volume flow rate divided by specific volume at the inlet is equal to mass flow rate at the exit, that is area of the exit, velocity at the exit divided by specific volume at the exit. So the ideal gas equation for the inlet is given as Pi Vi is equal to RTI, where specific volume at the inlet can be calculated with the formula Vi is equal to RTI over Pi. specific volume at the inlet is calculated here. 0.287 into 17. Here we have converted Celsius temperature into Kelvin scale temperature. So that is the value of Vi. Similarly, equation of state at the exit point is PEVE is equal to RTE, and the specific volume at the exit is RTE over PE, whose value come out to be 0.8479. So mass flow rate at the inlet is m dot I is equal to volume flow rate at the inlet divided by specific volume at the inlet, and mass flow rate at the inlet is 0.3 kg per second. Velocity at the exit is equal to mass flow rate into specific volume at the exit divided by the area of exit. So mass flow rate we have just calculated, put here, and the velocity at the duct or at the exit is 6.36 meter per second. That was asked in the questions. So there are basic two approaches to solve the steady flow energy equation. So the first one is Lagrangian approach and the second one is Eulerian approach. In Lagrangian approach, the position vary with time. As the time changes, the value, so you can, that is certain pipe. For example, this is the point or position 1. So we will say that any particle, let's suppose who is passing through point 1 has a mass flow rate of 25 kg per second. So in Eulerian approach, this is fixed. With the passage of time, the mass flow rate at a fixed position will be fixed. The property is fixed. However, in Lagrangian approach, the position varies with time. Sometime when we measure a mass flow rate at the specific position, the value of mass flow rate will change. That is why Lagrangian approach is complex to analyze, whereas Eulerian approach is easy to analyze. Therefore, we will be using Eulerian approach for our analysis. We will be deriving steady flow energy equation with the help of first law of thermodynamics for open system. Now, for steady flow energy equation, energy of the system is constant because we are studying the steady flow. In the previous slide, I have discussed in the steady flow, the energy of the system remains constant. That is, energy at the inlet is equal to energy at the outlet. Now, consider the figure shown on the right hand side. This is a vessel in which mass flow rate mass is coming from here and mass is exiting from here. I will write inlet and outlet. Inlet and outlet. This is outlet. So, and you can see that shaft work is extracted from the process, or you can see that is a turbine. Mass entering from the inlet provide energy for the rotation of turbine, which will produce a shaft work, which is then that is connected to the generator and produce electricity. So the work is extracted from the process, work is outward. So, and Q amount of energy is provided from down here, Q, you can see that. So, energy at the inlet, Q dot, that is provided here, m dot g z dot. So, m dot 1, m dot inlet. So, as it is a steady flow process, therefore, m dot I is equal to m dot E. M in is equal to m dot out. So, in our discussion, we will only be using m dot because mass flow rate is equal to mass flow rate in is equal to mass flow rate out. Now, Q dot plus m dot g z dot. What is this? This is the energy due to potential. Half m dot c1 square. This is due to potential energy. As this mass is entering from a height z, let's suppose that is z height, that is z1. Due to this height, there will be some potential energy stored in the fluid that will be entering from the inlet. Similarly, that is the height at exit, that will be represented by Z2. And internal energy, the fluid already have some internal energy, so that is due to the kinetic energy, and that is an internal energy. So that is work done, shaft work done. That is internal energy at the exit, that is kinetic energy at exit, that is potential energy at the exit point. Now that shaft work is equal to minus P1 V1 dot plus WCV plus P2 V2 dot. We will insert this value here, that the value of shaft work inserted in the form of control volume work here. Now the equation becomes Q dot plus m dot g z1 m dot g z1 plus half m dot c1 square, that is the kinetic energy at the inlet, u dot 1 internal energy at the inlet, is equal to minus P1 V1 dot plus WCV plus P2 V2 dot plus U2 internal energy at the exit plus kinetic energy at the exit plus potential energy at the exit. So we will simplify some terms, will come to left side and the equation become Q dot plus mgz1 plus kinetic energy plus internal energy. This term P1 V1 dot we have shifted to left hand side and the sign is positive. And the right side is W control volume, U2 plus P2 V2 dot, kinetic energy and potential energy. Now we know from the relation that enthalpy is equal to sum of internal energy and pressure volume. So we have divided this equation. Let me write this. We know that enthalpy is equal to U plus PV. We have divided all the side with seconds, time. So we have obtained this relation. The symbol dot means that the term is divided with the time. So when Q dot is mentioned, it means heat flow rate, and the unit of this equation is watt, kilojoule per second or watt. So the above equation we have replaced the values of H dot 1 and H dot 2 on both the side, left hand side and right hand side. Now for unit mass system, capital Q dot is equal to m dot q. We have divided the entire equation with the mass. So this Q is equal to Q dot divided by m dot. So as we have divided the entire both hand side with the mass flow rate, so we have obtained this equation. Divide by m dot, mass flow rate. So both these equations are very important. You should remember these equations because this is known as steady flow energy equation for open volume. So you should also remember the units of these equation. For capital Q dot, the equation is kilojoule per second, or you can say that it is equal to watt. Sometimes it will be mentioned as power as well in the numerical problem. However, when small q is used, that means the unit is kilojoule per kg. It depends upon in which unit enthalpy is given to us, velocity and elevation. Z depicts the height or elevation. I must write it here. Elevation for potential energy. So this depends what sort of units or problem is introduced to us, then we will decide which of these equations we should use for our problem solving. Conceptual question. A mass flow rate into a control volume requires a normal velocity component. Why? The answer is tangential velocity component does not bring any substance across the control volume surface as it flows parallel to it. The normal component of velocity brings substance in or out of the control volume according to its sign. The normal component must be into the control volume to bring mass in. Just when you enter a bus, it does not help that you run parallel to the bus. What it is saying that as velocity is a vector, it has two components. That is normal and that is tangential. So this is a pipe, then that is the cross sectional area. So the normal component is responsible for the mass flow rate into the cross sectional area of the pipe. That is why the normal velocity component is required for control volume for a mass flow rate. Steady flow energy equation versus Bernoulli's equation. The steady flow energy equation is given by Q plus Gz1 plus half C1 square plus H1 is equal to control volume work plus H2 plus half C2 square plus Gz2, where Gz1 and Gz2 are potential energy component and half C1 square and half C2 square are kinetic energy component, and the unit is given by kilojoule per kg. Steady flow energy equation is valid for both compressible and incompressible fluids. Compressible and incompressible, that means gases and liquid both, gas plus liquid. And Bernoulli's equation is only valid for incompressible fluid. That means Bernoulli is only valid for liquid. Assumption for incompressible fluid. There are certain assumptions for Bernoulli's equation. Incompressible fluids mean liquids. T is equal to constant. That means temperature throughout the process will remain constant. No work interaction. That means control volume work will be equal to 0. There will be no change in the volume. Therefore, delta V is equal to 0. No heat interaction. No heat interaction. This means that Q is equal to 0. Therefore, when we applied all the assumptions to the steady flow energy equation, we get this equation as a finalized form, and the unit are still in kilojoule per kg. Now, this is the equation from the previous slide. We can write this in the differential form as C is the velocity, D is the symbol of derivation, and C is the velocity. G dz. G is the gravitational acceleration change into change in the elevation or height. dH, change in enthalpy. So this is the same equation, but we have write this equation in the differential form. When we integrate this equation, we will obtain the previous equation. Now, from the relation, we know that H is equal to U plus PV. We take the derivative on both hand side. We will get dH plus du plus dPV. So dH is equal to du plus PdV plus VdP. Here we have used the product rule, product formula for derivation. So first derivative of second plus second derivative of first. So as there is no change in volume, and no change in temperature, therefore du and pdv will be cancelled out and dH will be equal to vdp. So we will insert this value here and we get this relation CdC plus GdZ plus VdP is equal to 0. Now we will integrate the above expression and we will get this expression. Change in kinetic energy plus change in potential energy plus specific volume into change in pressure is equal to 0. As we know that specific volume is equal to 1 over density, we put the value here, so that is change in kinetic energy, change in potential energy and change in pressure. That is equal to constant. Therefore we have for the inlet and outlet value we have separated on the both hand side, so the value is kinetic energy, potential energy and pressure is equal to constant. This is known as Bernoulli equation. Conceptual questions. Can a steady device have boundary work? Answer: no. Any change in size of control volume would require either a change in mass inside or change in state inside, neither of which is possible in a steady state process. So as you know, for boundary work, steady flow process, so there will be, if we want to have a boundary work in a steady flow process, then it will require a change in size of control volume. But in Eulerian approach, we have fixed that the mass flow rate inside is also fixed. Therefore, the boundary work in steady device is not possible. Question: what can you say about change in m dot and v dot through a steady state flow device? So answer: according to continuity equation, mass flow rate at the inlet and outlet is same for single flow device. That is the basic assumption for steady flow process. Mass flow rate at inlet is equal to mass flow rate at the outlet. However, the volume flow rate can vary if the state changes, then V changes. For a constant mass flow rate, V mass flow rate equal to volume flow rate is equal to specific volume into mass flow rate. So as this is constant, so volume flow rate can vary, because if the state changes then specific volume change, this will change, therefore this will also change, mass volume flow rate will also change. Conceptual question: if you want to determine a state property in multiple device flow system, where should you look for information, upstream or downstream? First, you should know what is meant by upstream and what is meant by downstream. Upstream means at the inlet and downstream means at the outlet. So if you want to determine the state property in multiple device flow system, so where you should look for, the answer is generally a flow is affected more in downstream than upstream. So flow is more affected at the outlet. Than inlet. So generally we will look at the outlet. The second point states that only pressure information can travel upstream in subsonic flow. If the flow velocity exceeds the speed of sound even, then pressure information cannot travel upstream. So it is saying that if the flow is subsonic, we will discuss about what is subsonic and what is supersonic in upcoming slide when we discuss about the nozzle. So you should know that the pressure information, when the flow velocity is very low, less than the speed of sound, then only pressure information can you study at the inlet, and if the flow velocity is greater, then even a pressure information cannot travel to inlet. Third point states that temperature at given location is mainly given by the upstream conditions. Now for temperature, upstream means inlet, and influenced very little by downstream means outlet. So the summary of these 3 points is generally when you are looking for property value, you should look at the outlet. For pressure, you should definitely look at the outlet. But for temperature, you should look at the inlet. So there is no hard and fast rule that for every property you have a fixed position to look for, either inlet or outlet. Rather, this differs for every property. For pressure, you have to look at the outlet, whereas for temperature, you have to look at the inlet. Introduction to nozzles and diffuser. There are two main topics in thermodynamics: nozzles and diffusers. So what are nozzles? It is a device that accelerates fluid. During this process, the velocity of the fluid is increased and pressure is decreased or reduced. It is an isentropic device. What is an isentropic process? The process in which the entropy of the system remains constant. Therefore, fluid passing through nozzles, entropy of the fluid remains constant. Nozzles can be used by jets and rockets to provide extra thrust. That is application of nozzles. So this is there are different types of nozzle, and one of them can also be used in jets and rockets to provide extra thrust, used in rocket propulsion as well. Now for diffuser. Diffusers are the device which slows down the fluid. That means velocity of the fluid is decreased with the increase in the pressure. So nozzle and diffuser are opposite devices to each other. Nozzle accelerates the fluid, whereas diffuser slows down the fluid. Now the similarity lies here. Both are isentropic devices. That means the fluid flowing through nozzles and diffuser, both of their entropies remain constant. Many jet engines use diffuser to slow air incoming into the engine for more uniform flow. So as the function of diffuser is to decrease the velocity, so jet engine use diffuser to slow down, to decrease the velocity of air, so that there is a uniform flow of gases and combustion can be performed more. Mach number. What is Mach number? It is the ratio of velocity of object to the speed of sound. Mach number formula is written as Mach number is equal to velocity of fluid divided by velocity of sound. So generally in meter per second and standard temperature and pressure, the velocity of sound is 340 meter per second. So if fluid velocity, if you want to check the Mach number, then velocity of fluid divided by velocity of sound. This value is at standard temperature and pressure, so the velocity of sound changes with the temperature. Now there are three cases a Mach number can comes out to be. Case 1. If we divide a velocity of a fluid with the velocity of sound and Mach number comes out to be less than 1, then the flow is called subsonic flow. The tap water is an example of subsonic flow because the velocity of water coming out of the tap is less than the speed of sound. Case number 2. If the velocity of the fluid flowing through a pipe is equal to the velocity of sound, then the flow is termed as sonic flow. Case number 3. If the velocity of fluid exceeds the velocity of sound, that means the velocity of fluid is greater than the velocity of sound, then the flow is termed as supersonic flow. So in rocket propulsion, as mentioned in the previous slide, in rockets and jets, supersonic flow through nozzle occur in which the Mach number is greater than 1. So nozzles, subsonic flow. So in subsonic flow, this is the schematic diagram of nozzle. You can see that. Subsonic flow means if we represent Mach number with m, then it means Mach number is less than 1. That means subsonic flow, the velocity of the fluid is less than the velocity of sound. So C1 and fluid getting out is C2. That means C1 is very smaller than mass flow rate through this nozzle is less than the speed of sound. Now if the flow is supersonic, then the schematic diagram of nozzle will be this. For supersonic flow, m is greater than 1. So if we want to increase the velocity again, then this type of nozzle is used, where the inlet area AI, okay, I will write it at the bottom. So this is the inlet area, that is AI, and that is the AO. So in supersonic nozzle, AI is less than AO, whereas subsonic nozzle, A inlet area is greater than outlet area. Now, convergent divergent nozzle. If you have a flow whose velocity is less than speed of sound, then here flow will be subsonic. So this portion will act as a subsonic nozzle. So it is designed such that the flow at the intersection becomes Mach is equal to 1, and in this section the flow will be supersonic. So for example, a fluid is entered with a velocity of 100 meter per second. So the fluid will accelerate through this portion. When it reached the intersection point, the velocity will increase up to 340 meter per second, and this portion as well will act as a supersonic nozzle. So the velocity will kept on increasing, and V out will be very greater than, much greater than velocity at the inlet. So I hope you understood the concept of convergent divergent nozzle. They are the combination of subsonic and supersonic nozzles. The first portion will act as a subsonic nozzle, whereas the second portion will act as a supersonic nozzle. So in this, for the entire portion from inlet to outlet, speed will increase or velocity will increase. What are diffusers? Diffuser decrease velocity, increase pressure. Similar to nozzles, there are three types of diffuser. Now, what is the function of diffuser? To decrease the velocity. A high velocity fluid will enter C in, whereas a low velocity fluid will come out. This is the schematic diagram of diffuser. Now, as this is a subsonic diffuser, therefore fluid flowing through the diffuser has Mach number less than 1. So let's suppose the velocity of the fluid incoming is 300, which is less than the speed of sound. Then the fluid velocity coming out will be like 50 meter per second. Supersonic diffuser. Also here you should know that area at the inlet is less than area at the outlet. Similarly, area at the inlet is greater than area. So supersonic diffuser, Mach number is greater than 1 because fluid flowing through it has speed greater than the speed of sound. So if C in has a velocity of 400 meter per second, then the speed will be reduced and C out will be 100 meter per second. Convergent divergent diffuser. Similar to convergent divergent nozzle, the function of convergent divergent diffuser is also the same, to decrease the velocity of the fluid throughout the section. So if the velocity of fluid here entering, as its function is to decrease the velocity, let's suppose now this portion will act as a supersonic diffuser, supersonic diffuser and subsonic diffuser. So the velocity of fluid entering, let's suppose it is 700 meter per second. So it is designed such that at the intersection Mach number is equal to 1. So velocity will reduce up to the intersection, the velocity is 340 meter per second. So in this portion as well, the velocity will keep on decreasing and the fluid comes out to be 50 meter per second. All these value is for example. This is not a harsh rule that the fluid will be coming at the inlet of supersonic diffuser at 700 and comes out to be 50 meter per second. So it is for explanation purpose only. When we will solve the problem, we will see in details how to solve the problems of nozzles, diffuser, where they are used, and that's on. This is an introduction to nozzle and diffuser. So hope you should know what are the schematics diagram, different type of nozzle. If you given what is this type of nozzle, you should know that the inlet area is greater than outlet area, so it is a subsonic nozzle. And similarly, if you are given what type of diffuser, this inlet area is less than outlet area, so diffuser is subsonic diffuser. So you should know the schematic diagrams of nozzles and diffuser and what are their functionality. For nozzle it is to increase the velocity of the fluid, for diffuser it is to decrease the velocity of the fluid. Different types of fluid flow, subsonic flow, supersonic flow, what are the types of nozzle for supersonic, subsonic flow, what is convergent divergent nozzle. You should remember this, and when we will solve the question answer numerical problem, we will see what type of nozzle and diffuser should we use to incorporate our problem. So home assignment for lecture 5. All students are advised to go through example problems for each topic discussed in this lecture. All students must submit handwritten lecture summary report minimum of 3 pages before the commencement of next lecture. Student can take picture and scan report and send it to my email address at aslan@ciitwa.edu.pk. All students are advised to keep hard copies of every assignment and report, as they have to submit them later when they will come to university for examination. All students are advised to prepare previous lecture thoroughly before the online video session, as there will be viva oral question answer session for every student. Thank you students for listening, and take care and keep safe. Keep yourself safe and keep others safe as well. Thank you.